So let me take a few minutes now to share with you some integral properties that might help you when you evaluate integrals. And the first is some integrals represent geometric regions. For example, if you're asked to integrate the square root function, the square root function is a V-shaped graph, and the area underneath it are triangles. So if you want to integrate the absolute value of x from -3 to 4, you can think about using geometry. This triangle is a 3 by 3 triangle, so its area is 1/2 3 times 3. That triangle is also a right triangle. Its dimensions are 4 by 4. So its area is 1/2 4 times 4, and the grand total is 12.5. So we didn't have to get an antiderivative here. Instead, we used geometry. In a similar fashion, here is an integral, the absolute value of x minus 2. It's just the absolute value graph shifted to the right 2. So you could draw a quick sketch. Its bounds are 0 to 5. So now we're getting two triangles whose areas are 1/2 2 times 2 and 1/2 3 times 3, with a result of 6.5. In this third example, this expression right here maps out a semicircle. You might remember from your algebra days that to draw a complete circle, you would use a plus and minus sign. The plus sign does the top of the circle, centered at the origin, and the minus sign does the bottom of the circle. And the radius here would be 5. I guess that should be an x, not an r. And the radius is 5, and here's a picture of the semicircle. If we're integrating from 0 to 5, we're actually getting the area of a quarter circle. So you just do 1/4 pi r squared, and you have your area. So why don't you try one now? Try this one. You can pause the video, and then when you've done it, you can check your answer. I'll go ahead and do it now as well. So this is a semicircle. And we're collecting all the area from -3 to 3. So we're doing the full semicircle, and its radius is 3. So we get 9/2 pi. Another thing you can be on the lookout for are symmetric functions. If a function is made up entirely of odd-numbered terms, odd-powered terms, then it exhibits rotational symmetry around the origin. And you can see this function has a cubic, a x to the first, and a sine function, which is also an odd function. So as a result, if you collect area from a negative value to its corresponding positive value, those areas cancel out. So any integral from a negative value to a positive corresponding value will be 0. And then even functions have a slightly different form of symmetry. An even function has y-axis symmetry. So any terms that have just even powers, x to the second, x to the fourth, 3x to the 0, which is also an even function, and the cosine is also an even function. If it's comprised entirely of even function terms, then the integral of an entire region from a negative value to its corresponding positive value would be twice the integral of just 1/2 of the region. So you can try a couple here. You could pause the video, but I'll go ahead and work these out. The tangent function is actually an odd function because it's an odd function divided by an even function, sine over cosine. So if you integrate from a negative value to its corresponding positive value, that area will be 0. The absolute value function is an even function, so it'll be equal to 2 times the integral from 0 to 6 under the absolute value function. And this is a triangle which has dimensions 6 and 6, so it's going to be 1/2 6 times 6, which is 18, and 18 times 2 is 36. All right. Something else that happens with functions is you can shift them vertically, and that introduces rectangular areas. So here's a function 4 sine 1/3 x, and its area is 24. If you integrate this from 0 to 3 pi, you get 24, as I've noted down here. And you could do that with u substitution, but what I want to focus on now is what happens if you add 2 to this function. So if you add 2 to this function, you shift it vertically. So now the function is 2 units higher than it used to be, and that introduces, in the same interval, a rectangle underneath. And the dimensions of that rectangle are 3 pi horizontally and 2 vertically. So we were adding 6 pi to the answer. So our new area now is 6 pi plus 24. And you can see that by taking the original integral and splitting it into 2. When you're adding two terms in an integral, you can integrate each part separately. So there's the first integral, 0 to 3 pi, and you're integrating 2, and then 0 to 3 pi, you're integrating f of x. This result is 24, This piece right here is that rectangle. It has a height of 2 and a length of 3 pi. So there's the 6 pi. And the entire area is 6 pi plus 24. So let's try that idea over here. Again, you can pause the video. I'm going to go ahead, though, and present the solution. I'm going to split this into two integrals. So here, I'm going to get 5. And then in the other integral, I'm going to get the absolute value of x. And now I'm going to do each of these geometrically. This part is a rectangle with a length of 6 and a height of 5. That's an area of 30. And then this is two triangles, one that's 2 by 2, so 1/2 2 times 2, and the other one that's 1/2 4 times 4. And I guess that grand total is 30 plus 2 plus 8, which is 40. So again, we evaluated this integral without doing any, quote, calculus, any antiderivatives. Instead, we just used our knowledge of geometry. And we can do the same thing here. We can split this into two integrals. And then we're going to evaluate each of them using geometry. And this first area is a rectangle. It's 8 by 7, which is 56. And then this is a semicircle of radius 4. So its area is 1/2 pi times 4 squared. And that gives you 56 plus 8 pi. You can also shift functions horizontally. And you take advantage of the shifts to evaluate integrals. So again, here's the same function with an area of 24. If I shift it to the right, pi over 2, then my function is x minus pi over 2. That's the argument of my new function. And if you integrate this from those shifted bounds, so now pi over 2 to 7 pi over 2, you should again get 24 because the horizontal shift doesn't add any area to it. And you could also get that result by using u substitution. So if I see that, if I let u equal x minus pi over 2, then du is dx, and I get back to this expression. Also if I change my bounds. So let's try that down here. I'm integrating the absolute value of x minus 4, and what I can do is shift that left 4, so now I'm just integrating the absolute value of x, and then I can shift the bounds left 4, so I'm integrating from 0 to 6. And then that result is 1/2 times 6 times 6. It's a triangle. And then the area is 18. So if you shift horizontally, as long as you shift the bounds and shift your function, then you are preserving the area. And then a comment on bounds. If you switch the bounds on an integral, you negate the value of the result. So the integral from a to b of a function will equal negative the integral from b to a of that same function. And I like to think about that in the context of displacement. If you integrate a velocity function from time 1 to time 2, you get a result. That's how far the car moved. But if you reverse time and you watch it play backward, then you're going from time 2 back to time 1. The car will move in the opposite direction, so its displacement will be negative. So switching the bounds negates your result. And I prefer my integrals to have larger upper bounds. I don't like seeing the integral from 4 to 1. I like seeing the integral from 1 to 4. So if I see the bounds this way, I switch them, negate my answer, and then proceed accordingly. So again, on a problem like this, I don't like that upper bound being smaller than the lower bound, so I throw a negative sign out in front and switch the bounds. And then I'm more comfortable handling my integral. And when I solve this, I get negative sine of x, and I'm evaluating the sine of x at pi over 2 and pi over 6 and subtracting, so I get negative, and then I get 1 minus 1/2. So my final answer is negative 1/2. And then something else that you can do geometrically is sketch antiderivatives. And we did this with a problem of the day, but I'll do another example here. So what we're going to do here is we're going to plot an initial condition and then use areas to plot more points on the antiderivative, and then connect those points to actually draw the antiderivative. And we're going to draw its concavity using the slopes on the given function. So here's the function, and we're going to sketch the antiderivative with the initial condition -2, 5. So I'm going to plot the point -2, 5, or somewhere up around here. That's the initial condition. And then what I'm going to do is collect area and draw subsequent points. Now this area is a semicircle with a radius of 2, so that's going to be 1/2 pi times 2 squared, or 2 pi. So this point has to drop 6 units on its from going from here to here. And if you drop 6 units, actually I'm going to backtrack here. Let me just do the quarter circle first. That quarter circle has an area of pi. So from time -2 to time 0, my function has to drop a length of pi, which is about 3. So it's going to be here a little more than 3, so it's going to end up right around here. That's a drop of 3 on the journey from -2 to 0. Again, this area is pi, so I'm going to drop another 3, 1, 2, 3, and a little bit, and I'm going to end up here. And then this area looks like an area of 1, so I'm going to increase by 1. And then this area is an area of 2, so I'm going to increase by 2 more and end up around here. And now I'm going to collect those points with the appropriate concavity. So because the slope of this graph is negative, I'm going to be concave down. The slope of the graph here from 0 to 2 is positive, so I'm going to be concave up. Positive slope, concave up. Negative slope, concave down. So I'm drawing a picture of the antiderivative. Now I can even go backwards in time. The area of this triangle off to the left here, it's a 4/2 triangle, so that's an area of 4. And that's positive area, so my function must be increasing, but I'm going back in time, so I'm going to subtract 4, and that would put me at a y value of about 1 over here. And I would connect those with a negative concavity because the slope of that function is negative. So there is a picture of the integral of f. So I have drawn basically here this new function g, which is the integral of f. And I started at the point 5, and I collected area from -2 to later points. So that's the function I just drew. What would happen if the initial condition were -2, 6? Suppose my initial condition were up here. Then the entire graph would look the same, would have the same shape. It would just be a vertical shift of 1 unit. So the entire graph would be vertically shifted 1 unit. I'll let you try the second example. The second example is a little cleaner in that there's no semicircle, so your areas tend to be whole numbers, but you can also try that one. So I want you to sketch the antiderivative of f. I want you to sketch g. I want you to start at 0 and give the initial y value -3, the initial value on g -3. So your initial condition, your initial point, would be down here at -3. And then you collect area, and that would tell you how far to rise and fall as you draw your subsequent points. The final thing I want to comment on is just a BC topic. There are some functions that don't have antiderivatives. At least mathematicians haven't found the antiderivatives yet. And this is a classic example, e to the x squared. There is no known function whose derivative is e to the x squared. So there's no antiderivative that we can write here. And what you can do in that case is you can model this function as a series. So that's what I'm going to do here. The series for e to the x looks like this. And it was a series that you learned back over the summer and you've used off and on over the course of the first part of our course. It looks like that. That's a factorial plus ... So what I'm going to do is build the series for e to the x squared and then integrate it. So here is the series for e to the x squared. What I have to do is replace every x here with x squared. So that x becomes x squared. This x becomes x squared and it's being squared. This x is x squared and it's being cubed. And then this x is x squared and it's being raised to the 4th. And that's what I wrote down here. So in brackets, I wrote those terms, 1 plus x squared plus 1 over 2 factorial x squared squared plus 1 over 3 factorial x squared cubed, etc. I'll clean up the power so I can use the power rule. X squared squared becomes x to the fourth. X squared cubed becomes x to the sixth. X squared to the fourth becomes x to the eighth. So now I've created a series of terms that I can just apply the power rule to. And of course, we're doing the power rule in reverse. So 1 becomes x squared becomes 1/3 x cubed. This becomes 1/5 x to the fifth with its fraction in front, etc., etc. And now we have a series that represents the antiderivative of e to the x squared. And this is what your calculator does when it calculates out values. It doesn't know this function e. Instead, it uses powers of x, and it just uses enough terms to achieve the desired accuracy. And we're going to explore that more later in the year. So now why don't you try? Maybe in a minute I will do this first one, just so you can compare your work. But you could pause the video now and try this. But I'm going to go ahead and share with you what that solution would be. So cosine of x squared has no antiderivative. So I'm going to take the cosine series and then build a series for cosine of x squared. So here's the cosine series. And again, this is a series that you worked with at the beginning of the year and off and on over the past few months. It only has even powers of x because cosine is an even function, and then it alternates sign. So now the cosine series for x squared, we have to replace all these x's with x squared and then keep the power on the outside. So it's going to look something like this, and then it keeps on going. And if you clean that up, that power is x to the fourth. The next power is x to the eighth, and the next power is x to the 12th. So the powers are growing by 4 every time. And now we can integrate. So the integral of cosine of x squared dx, we're just going to integrate this term by term, and we get x, 1 over 2 factorial 1/5 x to the fifth, plus 1 over 4 factorial 1/9 x to the ninth. Whoops, this should be a minus sign here. Minus 1 over 6 factorial 1/13 x to the 13th. And you could keep going, and then remember just that there's a possibility of a constant at the very end. So that's it. I hope that was helpful.